Since ancient times, hydropower has been supplying us with flexible, dependable and low-emission mechanical energy and, more recently, electrical energy. The materials of construction may have changed, but the technologies that we use in hydropower are well known, and hence the evolution of hydropower is potentially limited. Changes in the water system due to climate change also pose a threat towards the future of hydropower across the world. Most of the current hydropower generation relies on sites with a big elevation difference. But more recently, the trend of hydropower technology is moving towards exploiting resources with 2 to 20 metres of elevation difference. The pressure difference resulting from a difference in water height is called the head, and so these sites with small elevation differences are called very low head resources. These type of resources are commonly seen in small dams, rivers and various water conduits around the world. In a conventional hydro dam, you might see one of 3 turbine designs, depending on the water head and the water flow rate. The Pelton turbine works best with high head and low flow rates. It blasts a jet of water in a series of buckets on a wheel. The change in water direction is what imparts the force and causes the wheel to spin and turn a generator. The Kaplan turbine works best with low head and high flow rates. It works just like a boat's propeller in reverse. Here, the water flows past the propeller, generating a difference in pressure in the water stream, causing it to spin and turn a generator. The Francis turbine works in between, with moderate head and moderate flow rates. It is the most common type of water turbine used today. It looks a little bit like a rotor on a jet engine and uses principles of both the Pelton and Kaplan designs. But these conventional turbines cannot extract the energy from low head resources efficiently. We will need different designs to efficiently extract energy from very low head resources. One of the examples of low head turbine design includes the Archimedean screw turbine, which can be applied in 1 to 10 metre head difference and low flow rates of between 0.01 to 10 cubic metres per second. A study in 2007 estimates that the development of low head resources could nearly double the hydropower generation in the United States of America. Other improvements in hydropower generation includes material research and development to reduce the impact of abrasive particles in sediment-rich flows. The solution includes ceramic coatings on steel surfaces. This can reduce the operation and maintenance cost, hence improving hydropower's cost of electricity. Research and development to minimise the hydropower's environmental impact is also happening at the moment. This includes the fish-friendly turbine design, which provides a safe approach for aquatic life passing through the turbine. Innovation in tunnelling and dam technology also aims to reduce the environmental and visual impact, as well as reducing capital costs of hydropower projects. Another issue that has to be considered in the future of hydropower is the volatility of future water resources due to climate change. Using 12 climate models, scientists from the Norwegian University of Science and Technology at Trondheim found out that although the overall change is small, by 2050, various regions may experience significant changes of water runoff. This will affect their hydropower output. For example, several regions with high dependence on hydropower, such as Southern Africa, might experience up to a 70 gigawatt hour per year decrease in hydropower generation, while Northern Europe, East Africa and Southeast Asia might actually see increasing generation. Despite being a mature technology, we can still see improvements in hydropower generation. These innovations will enable us to exploit potentials from low head resources, decrease the cost and reduce the negative environmental impact of hydropower. Better climate modelling will also allow us to more accurately predict the best locations in a changing climate. So, the way we harness energy from water might not change radically in the future, but the incremental improvements will make future hydropower much more sustainable.